Alright, gang, here we go. This is for Physics, Unit 10, Part 1, talking about magnets and magnetism. This is it. You've made it to the last unit of physics. You should give yourself a pat on the back. It's just a little bit more. One more unit, a couple quizzes, an exam, and final, you're done. Dunzo. Out of here. Okay, so you can do it. Alright, so we're going to learn all about magnets. Okay, how do they work? Why do they work? So on and so forth. You've probably played with magnets quite a bit, right? Now, you should have known whether you have like a horseshoe magnet that looks kind of like a horseshoe or just a bar magnet, okay, like this, and even like a circle magnet, like a fridge magnet. They always have what's called a north pole and a south pole. Okay, like north and south, sometimes they're labeled. On a circle magnet like this, it's actually the top and the bottom that's the north and the south. Kind of interesting. Okay, but anyway, they always have a north pole and a south pole. Okay, and these two poles act kind of like the positive and negative of electric charges that we just talked about. You know, if they're the same pole, so a north and a north and a south and a south, they repel each other. Okay, they push each other apart from one another if they're the same pole. If they're opposite poles, then they attract each other. Okay, opposites attract. Okay, things that can act like metals are referred to as ferromagnetic. Now, this comes from when we first started discovering magnets. First set of magnets we really made were made out of iron, and ferrous is iron, so that's where we kind of get this term ferromagnetic. So not all magnets are made out of iron, right? But we call them ferromagnetic. Okay, and so we also know, and this is pretty standard idea here, is that if we take a magnet and we suspend it from a string, so here's a bar magnet that we're suspending from a string, and it can just rotate freely, and we say, well, this one's north, this one's south, it's always going to rotate itself so that this end is pointing towards the North Pole. Okay, and that's just how compasses work, and we'll talk about why that occurs here. Okay. Inside every molecule or inside every compound, it doesn't matter what you're talking about, it has what are called magnetic domains. Okay, and so there are like little lines here or something like that you can't quite see, but or at least maybe you can see them, I can't quite see them. But anyway, so you get these things called magnetic domains, and these magnetic domains, what they are regions in which the electrons that are making up this metal are all spinning in the same direction. Okay, and so if you remember from your Chem 1 days, or maybe you took Chem 2 or AP Chem, you remember that we can have our electrons, they can spin one of two ways. They get an ms, or a atomic number ms, of either plus 1/2 or minus 1/2. Right, and so essentially what we're saying here is that they're spinning kind of like a top. They're either spinning clockwise or counterclockwise, and so these regions are where our electrons have all managed to spin in the same direction. So in this area, all these electrons are spinning and pointing in generally this direction, and generally this direction, generally this direction, and so we call these regions, these domains, magnetic domains. All right, and so in most things that are out there, the domains are just randomly arranged, just kind of like this. The arrows are all pointed in different directions, so on and so forth. So like a paper clip or a nail, these things can act like magnets, right? They are ferromagnetic, but generally they're not magnets. Just normally, you don't pick up a paper clip and it's not magnetic. But if you bring a magnet close to a paper clip, you know that it'll attract that paper clip. And what occurs here is our paper clip its domains might start looking something like this, right? But when you bring another magnet close to it, its domains start to all get aligned in the same directions. Okay, and because they start getting aligned, all these electrons start getting pushed in the same directions, so they're all aligned like this, and so and this is really what creates that magnetic attraction between the two. All right, so in all magnets, especially those permanent ones, ones that don't lose their magnetism, those domains are stuck in this alignment. They can't unarrange themselves. Okay, so if you took a paper clip and you rubbed a paperclip repeatedly in one direction with the north pole of a magnet, right? Your domains would start to get better aligned, okay? And if you did a good enough job inside here, we kind of get this thing, right, that we just drew, where our paper clips, all those domains would be pointed in the same direction. And if you did a good enough job, and you did this long enough, these would get kind of more and more stuck in this location, and it would start acting like a magnet. So you could actually take that paper clip and use it to attract other paper clips. And so that's really, if you've played enough with magnets, you've seen this occur where you take something that's originally not a magnet itself, but it is attracted to magnets, and then you can all of a sudden you've turned it into a magnet. And this is kind of how we make magnets. Now the idea, if depending on how sticky the magnetism is in those domains, depends on how long it'll stay magnetized. Okay, so something like a paper clip, its domains don't stay in this arranged formation for very long. They're going to start rearranging themselves back into their random orientation after a while, and so these domains gradually become randomly oriented. And we can actually make that happen a little bit faster by like heating it, changing its temperature, heating and cooling it. Okay, we'll change it. We could also just by like beating it, like hammering it down flat, we can like hammering it, we can kind of knock those domains back into their random situation. Okay, so anything that can have, so essentially what we come down to now is back to this idea of ferromagnetism. Anything that's ferromagnetic is really things where we can make these domains align very easily. So things like things that are made out of iron and nickel and cobalt, they're ferromagnetic. All right. So we get lots of different types of magnetic materials. Soft magnetic materials, like iron, are easily magnetized, but they also lose their magnetism easily. Okay, so you can turn them into magnets, but they also don't stay magnetic for very long. It's things that are referred to as hard magnetic materials, for like nickel and cobalt. Okay, some other alloys like neodymium, they retain their magnetism for a long, long time just all by themselves. These domains that we're talking about don't reorient themselves very well. In order to get something to be magnetic, we use these things called a magnetizer. Okay, magnetizer. All right. And in these magnetizers, essentially what's going on is you've got two little boxes right here. And you can put your magnet in here, right? Your magnet like that. Okay, and you'd say like, well, that's my North Pole and that's my South Pole, and then you'd have your North Pole here of your other magnet, and then your South Pole over here, and then you'd stick this guy here on top of the two to create like a complete circuit. And then you plug this into the wall, right? There's our socket, right? Plug it into the wall, and then you turn it on, and then what it does is it induces a magnetic field through this thing, where it comes up the north, down to the south, and around the corner again, and creates this circuit. And we can actually create a magnet, or we can take these magnets and remagnetize them. So lots of schools do this for their magnets they use year on, year out, because you don't want to buy new magnets every time these magnets kind of go bad, right? They lose their magnetism. So even if you buy good ones that are hard magnetic materials, their magnetism still will go bad after a while, especially just using them to experiment with things. So, every time your magnet tries to induces magnetism on something else, it's going to lose a little bit of its magnetic stickiness. All right. So let's talk about magnetic fields. So how we know, like, if you take a magnet, right? If you take a magnet and so there's your North Pole, there's your South Pole, and you stick it next to a paper clip. Here's my paper clip, and you get it close enough, you know that this paper clip is going to just start moving towards it. Well, what kind of force is that? We know that force is a mass times acceleration. Paperclip has a mass and it's starting to move, so it's got acceleration. So that means there has to be some sort of force acting on this paperclip. Well, there's only a couple kinds of forces that we've learned about. It can't be a contact force, so it's got to be a field force, right? So because it's not directly touching it, so it has to be a field force. So we've talked about several different field forces so far. So how do we measure those field forces? Well, first field force we talked about was a gravitational field, right? And we could measure gravitational fields really, really easily just with any object. We release that object and then it falls in the direction of that field. We can calculate its acceleration just by how fast does the acceleration change, right? Or not how fast, but how fast does the velocity change? Because of that acceleration, F equals ma, right? And then what object is used to detect an electric field? Well, for an electric field, we're going to use a positive test charge particle, or positive test particle. Okay, and then we release it, it's always going to move in the direction of the field. Okay, and that's because a force is put on that test particle. So we just talked all about this. If our electric field is pointing this way and we put in a positive test charge particle, it's going to want to follow that way. All right, so the positive charge is always going to go with the electric field. Now, a magnetic field is a little bit different. All right, a magnetic field, we're going to use a compass to determine the presence and the strength of a magnetic field, or at least to detect the magnetic field. And in a compass, we always have a north pole and a south pole. So if we've got a little compass here, and you know, a lot of times, like the little ones you see in class are kind of shaped like this, and one side of it is painted red, right, for the North Pole, and that's always going to be pointed towards the North Pole. And so we can use this to help draw our magnetic fields. So here's a little bar magnet with our magnetic fields, and what they've done is they're just taking this compass and they're showing you what's going on here. Okay, and it shows the direction of the field. So as we move this compass out and around, we can kind of see what's going on. And notice that this line, if we just draw lines tangent to it, we get these compass lines, and so we can connect these lines together to show us what these magnetic fields are doing. Okay, we always draw magnetic field lines out of the north and into the south. Okay, out of the north into the south. All right, notice there should be something pretty clear here, that around the poles, okay, around the poles, we get a lot more magnetic field lines. Okay, the more, just like the electric field, the more poles you or the more lines you have in a given area, the stronger it is. All right. Another way to look at it is that the more distance you have between the field lines, the stronger it is. Okay, so out here, these are very far apart. The magnetic field is very weak. Here, the magnetic lines are very close together, so it's very strong. All right. Another interesting thing is these magnetic field lines actually exist within the magnet themselves. This is a little bit different than what we learned about with conductors. Remember, with a conductor, the electric field inside the conductor was actually zero, but inside something that's creating a magnetic field, the magnetic field still exists. Okay, so we usually don't draw it, but technically this magnetic field line would still be going straight through here, you know, straight through here, so on and so forth. These lines would kind of connect like this. You know, and so we usually don't draw it. Usually we just focus on these ones outside because it's hard to put things inside of a solid object. All right. Now, again, we just need to be able, just like everything else in physics, we need to be able, we can talk about things qualitatively, but we also need to be able to talk about things quantitatively. So we want to be able to use this idea called flux. All right, this is a really important concept that's going to come up over and over again throughout the rest of this unit. And flux is the idea of how much of a field is passing through a given area. Okay, and so you can imagine if we take like a ring, right, and we put that ring perpendicular to it right here. Okay, and so these magnetic field lines are passing through this ring. Your flux is a measure of how many lines are passing through it. Okay, and so if you take that same ring, same diameter and everything, and you transport it, you know, just translate it so it's down here, notice how it's got a lot more lines passing through it, so its flux is much higher. All right, and so essentially what this means is that we can develop this formula. Now this guy here, this symbol, right, is what we're going to use for flux, and specifically it's the magnetic flux. There's different kinds of fluxes, but we're going to focus on magnetic flux. All right, and it's equal to the surface area of the area that you're talking about times b cosine theta. All right, and b cosine theta is a term that helps us keep track of the magnetic field and the part of that magnetic field that's normal to the plane of the surface. Now, what do I need you to know about this? What I need you to know is just the definition of magnetic flux. Okay, its area and its times the magnetic field, or the component of the magnetic field that's perpendicular. Okay, last little bit here. Earth has its own giant magnetic field. Okay, and there's actually quite a bit of debate. It's kind of interesting to read about, like, well, what's causing the magnetic field of the Earth? Oh, you know what? There's something else I forgot to tell you about magnetic fields. I'm sorry. Jump back here a second. So we talked about they always go north to south, but here magnetic fields aren't just two-dimensional. They also appear in 3 dimensions. So we need to add a little notation here. Okay, for when we're messing with other magnetic fields. So if our magnetic field is in the plane of the page, okay, if our magnetic field is in plane, all right, so that's just flat with the page, we use an arrow, right? However, if it's going, we could also imagine, like if we took this magnet and we flipped it on its end, these magnetic fields would now be pointing in and out of the page. All right, so if the magnetic field is going into the page, okay, we're looking at the back of the arrow, so we're going to see an X. All right, and if it's coming out of the page, then we're going to see the front of the arrow, okay, and it's going to be a dot or a circle, okay. It's not going to let me draw this, but okay. So anyway, so in plane is an arrow, right, and then into the page is an X, out of the page is a circle, okay. Sorry, I almost forgot that. That would have been bad. Okay, Earth's magnetic field, okay, is actually quite a bit of debate about what's causing that. There is quite a bit of iron in Earth's crust, but it could also be caused by moving magnetic currents, or moving molten lava, which is really just metals that are moving around under the earth, and so on and so forth. All right, and that movement is causing it, and it makes more sense based on what's going on here, because actually what happens is there's been geographical data to prove that the magnetic field of the earth is actually flipped, and it flips occasionally, and the idea that these magnetic fields are being caused, or this magnetic field is being caused by moving molten lava underneath, kind of would support the idea that this magnetic field is not completely permanent. It also would help us explain why Earth's magnetic field is much, much stronger than Venus's. Earth has a much faster rotation speed than Venus does, which partially implied by caused by the movement of magma under Earth's crust. And so this magma is also causing this magnetic field. So if Venus is going slower, that means its magma is going slower, which means it's got a lower magnetic field. And our data about Venus also proves that. Okay. Another interesting thing is that the north pole of our magnet will always point to the North Pole. Okay, the geographic North Pole, but it's really the magnetic South Pole. So we've misnamed our magnets that we use for navigation. They actually point towards the magnetic South Pole. Not only that, but they're actually slightly different from one another. The magnetic and geographic poles are about 1,500 kilometers apart from one another. So that's quite the difference. So from here to here, that's about 1,500 kilometers. And so we use magnets all the time to help us navigate, but it's kind of we're just kind of fudging the numbers a little bit, okay, because they're going to be pointing towards the geographic North Pole, or just generally, but they'll be about 1,500 away from each other. It's kind of interesting. All right, so if you're in the U.S., okay, and you're using a compass, your needle is going to point toward the north, but slightly downward into the earth. So if you're ever holding a compass and you see it kind of like point down like a little bit, it's because it's being dragged into the earth, because sorry flat earthers, but the earth is round, and so it's wanting to take that straight line straight into the pole right there, straight through the crust. So it's going to be pointed down. All right. And these magnetic field lines are not parallel with the Earth's surface. See how they kind of come into and out of the pages here. Okay. And Earth's poles, like I said before, have reversed many times in the past. If that ever happens, for us, we're going to have to change some stuff. I'm sure birds get very, very confused because they use magnets to help them navigate. Okay, so on and so forth. And that's it for our unit here, or for part 1. Go ahead and do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.